All right, we're studying calculus now. I was looking for something more fun, and I do have physics, psychology, and business management to look into, but I need to learn calculus. Calculus and accounting are kind of priorities, so let's go ahead and tackle it. Bam. We're back to reviewing chapter one. Oh my God, there's already a typo. Introduction. Introduction. I don't know, this doesn't give me a great feeling about this. And literally in the previous section, you're talking about all the experience you had. Apparently, not much experience with grammar. I guess your expertise is numbers. That's fine. We'll see though. Chapter one, introduction. Introduction. 1.1, what are numbers? The irrational numbers. 1.2, decimals and real numbers. And 1.3, we'll be studying complex numbers, including operations on complex numbers. There's a total blank spot there, so maybe something else, and geometric representations of complex numbers. And then in 1.4, we'll be looking at count table sets, or count, oh my God, I can't read, countable sets. There's the coffee, that'll perk me up. 1.1, what are numbers? The irrational number, not irrational, sorry, the rational numbers. We have lots of kinds of numbers, but they all start with natural numbers, which are 1, 2, 3, and so on. If you can count your fingers and toes, okay, you know what? There's a lot of typos already. Whatever, for the sake of the video, I'll just power through. Fuck it. If you can count your fingers and toes, you'll come up with 20. Most of you will. And that is a natural number. We can, in our imagination, consider that these natural numbers go on forever, past a million, a billion, a trillion, and so on, to infinity and beyond. In elementary school, you studied not only these numbers, but how you can perform operations on them. What operations? There are addition, subtraction, multiplication, and division. You can add two natural numbers together and you will always get another natural number, as in the famous fact that 1 and 1 are 2. Subtraction, on the other hand, is trickier. If you subtract a number, for example, the number 5 from itself, you get something new, something that is not a natural number at all. We call it the number 0. And if you subtract number, again, say 5 from a smaller number, say 3, you get something else that is new, namely a negative integer, which in this case is -2, called -2. You can use numbers to count the number of pennies you have in your pocket. Thus, you might have 5 pennies in your pocket. 0 is the number of pennies you would have in your pocket if your pocket had a hole in it, and all those you put in immediately fell out again. Now, suppose you go to a store and the storekeeper is foolish enough to give you credit. Suppose further that you had 5 pennies and you bought some expensive item costing 11 pennies. Then the negative integer, -6, represents the fact that not only do you have no pennies, but if you got 6 more, you would be obligated to surrender them to pay for this item. 6 here is the number of pennies you would owe your creditor if you were to pay him your 5 pennies and he gave you the object and lent you the rest of the money. So to accommodate subtraction and to be able to represent amount owed by numbers, we extend the natural numbers to include the number 0 and the negatives of the natural numbers. This entire set of numbers, positive natural numbers, their negatives, and 0 is called a set of integers and is denoted by the letter Z. We can take any two members of Z and add them or subtract them, and in either case get another member of Z. I know all that, but I am very rusty on actual additions and subtractions. I get them wrong much of the time I try to do them. Most people will make a mistake roughly once in any 10 additions or subtractions of single digits that they perform. Damn, that's a lot. This means that if they add or subtract, I think we need better education then. Holy crap, it's bad. That is a horrible score. Terrible performance. This means that if they add or subtract numbers having many digits like 1, 2, 3, 4, 1, 2, 3, and 5, 4, 3, 2, 1, 2, 1, they stand an excellent chance of getting the wrong answer. Fortunately, that is of no significance today. You can easily check additions and subtractions on a calculator or on a spreadsheet and see if you get the same answer several different times. Unfortunately, I usually make an error in keying the numbers to add or subtract, or add instead of subtract, or do something else equally absurd. All that means today is that I must do every calculation at least 3 times to have a reasonable chance of correctness. True, the amount of my effort is triple what it might be, but 3 times very little effort is still very little effort. If you have this problem, you will be best off adding or subtracting on a spreadsheet. Then you can look at your computation and use your judgment as to whether it makes sense. Here are some rules for checking for sense. When you add positive numbers, the result should be bigger than both of the two summons SUMMANDS that you added. If one of the numbers is positive and one is negative, the magnitude, or the value, if you ignore the minus sign of the sum, should be smaller than the magnitude of the larger of the two. And the sign should be that of the summoned with the larger magnitude. Also, the least significant digits of your numbers should add or subtract correctly if you ignore the rest. If, for example, you subtract 431 from 512, then the last digit of the number had better be 1, which is 2 minus 1. If your checking produces something suspicious, try your computation again, but be more careful, particularly with the input data. The operation of subtracting 5 from another number undoes the operation of adding 5 to another number. Thus, if you do both operations, add 5 and then subtract 5, or vice versa, you're back where you started from. For example, 3 plus 5 minus 5 equals 3. Adding 5 and subtracting 5 are said to be inverse operations to one another because of this property. Performing them one after the other is equivalent to doing nothing. By the way, why isn't 0 a natural number? Let's find out. I have no idea. That's why people defined natural numbers long ago, and nobody cared much for changing that definition. Back in elementary school, you also encountered the notion of multiplication. This is something you can do to two integers, which will produce a third one called their product. You were, I hope, forced to learn a multiplication table, which gives the product of each pair of single-digit numbers, and then learned how to use this table to multiply numbers with more digits. I was never very good at this, says the imaginary student or whatever, I guess that's plugged into this. In olden days, you had to be able to do these things, additions and multiplications, if only to be able to handle money and to perform ordinary purchases without being swindled. Now you can use a calculator or a computer spreadsheet to do these things if you know how to enter integers and to push the plus or minus or multiplication and equals buttons as appropriate. Unfortunately, this fact has led pedagogues to believe they do not have to force pupils to go through the drudgery of learning the multiplication table. This does much harm to those who do not bother to do so because of the way our brains function. It turns out that the more time we spend on any activity as children, and even as adults, the bigger the area of the brain gets that is devoted to that activity, and the bigger it gets, the better we get at that activity. Thus, you're spending less time learning the multiplication table has the effect of reducing the area of your brain devoted to calculation, which impedes your further mathematical development. Facts. Your skill at mathematics will be directly proportional to the amount of time you choose to devote to thinking about it, and that is up to you. I would probably think about it more if math is more stimulating, more exciting. It's just literally the most boring subject. If it was more exciting, I'd pay more attention to it. You guys gotta feel like mathematicians and people teaching math have to make it more exciting. There's just nowadays there's so much stimulation. Like you got Instagram, you got social media, you got movies, you got shows, you got all this stuff, streaming, video games, where it's just like instant rewards and instant feedback, and math does not do that for you. And it seems like it hasn't really changed much. So people are less and less interested in it. relative to things that progressively get more and more stimulating all around them, except for apparently math. You think all you nerds, all you people that are super smart would be smart enough to come up with a way to make it more interesting? Oh, all right. Fuck. Maybe I'm the one that has to do that shit. Pick up the slack, carry the team. I got you. Again. All right. Once we are acquainted with multiplication, a natural question is, how can we undo multiplication? Division. What is the inverse operation? Say to multiplying 5 by 5, so that multiplying and then doing it is the same as doing nothing. The operation is called division. Yep. So you learn how to divide integers. The inverse operation to multiplying by x is dividing by x, unless x is 0. Now, here comes the problem. If we try to divide 5 by 3, we do not get an integer. So just as we had to extend the natural numbers to integers to accommodate the operation of subtraction, we have to extend our numbers from integers to include also ratios of integers, like 5/3. If we want to make division, we'll define for every pair of non-zero integers. And we want to be able to define division wherever we can. Ratios of integers are called rational numbers, and you get 1 for any pairs of integers, so long as the second integer called the denominator is not 0. Ratios like 5/3, which are not themselves integers, are called fractions. Once we have introduced fractions, we want to provide rules for adding and subtracting them and for multiplying and dividing them. These start to get complicated, but fortunately for us, we have calculators and spreadsheets that can do these things without complaining at all, if we have the wit to enter what we want done. This is still 1.1, damn it. Oh, okay. There's one thing we cannot do with our rational numbers, and that is to divide by 0. Division, after all, is the action of undoing multiplication. By multiplying any number, 0 gives result 0. There's no way to get back from this 0 product when you multiplied 0 to 0 by to get it. Of course, adding and multiplying and subtracting and dividing fractions is more complicated than doing so for integers. To multiply, say, a over b times c over d, the new numerator is the product of the old ones, namely ac, and the new denominator is the product of the old ones, bd, so the product's a over ac over bd is the same as a over b times c over d, which equals ac over bd. The inverse operation of multiplying by c over d is multiplying d over c, and that inverse is by definition the operation of dividing by c over d. The product of any number and its inverse is always 1. This means that d over d is always 1 for any d other than 0. Thus, a over b divided by c over d is a over b multiplied by the inverse of c over d, which is a over b multiplied by d over c. The answer is ad over bc. Adding is a bit trickier. The notion of addition can be applied to objects as well as to numbers in the following sense. We know, for example, that 3 plus 5 is 8. This means that if we have 3 radishes and dig up 5 more, we will have 8 radishes, assuming nobody has eaten the first 3. And the same is true for any other objects in place of radishes. This tells us how to add fractions that have the same denominator. Thus, 3 over a plus 5 over a is 8 over a, in which 1 over a has replaced a radish. We are applying the general rule for addition of things to the object 1 over a. To add fractions with different denominators, you must first change them so that the denominators are the same, then add the numerators like you are adding numbers. The easiest way to do this is to make the new denominator the product of the old ones. Thus, to find a over b plus c over d, first you multiply the first term by d over d and the second by b over b, getting ad over bd plus ab over bd. And the answer is AD plus CB over BD. You can do the same sort of thing for subtraction. Oh my God. You were probably forced to factor out common terms in the numerator and denominator in that answer in school, but you don't have to do that in entering the answer in a spreadsheet, which makes addition of fractions much easier when you use spreadsheets. All right, how long has this video gone on for? I feel like I've been doing this for like half an hour. 15 minutes. It's Jesus. Time goes so slow when you're doing math. All right. You know what? I'm bored and this isn't really helping me study. We'll come back to it. Let's look at the more interesting subjects.